And it's a thing of beauty. And this actually can explain base excess. So what you do is you start with a noughts and crosses slightly skew with when you draw like that. Put a few little normal things in. Okay, that's normal. What we've got here is CO2 buffer lines 7, 5, and 3. Okay, so what disturbance leads to the bicarb to drop initially, but the CO2 doesn't change? All you've got, and the first thing is bicarb going down. That is a
metabolic acidosis.
Okay, bicarb goes down, CO2 must go down. Remember, idiot proof. Bicarb goes down, CO2 must go down, and there it is going down. And actually, what you have here is a drop in the amount of bicarb in the system. So when you ask, do you have a base excess? You go, no, I've actually got a base deficit that I would have to replace base to get there, and that's where people talk about negative base excess. In West, he talks more complicated about parallel lines, but the end result is in metabolic acidosis, you have a negative base excess. What's this condition? You see that one coming? The CO2 is dropping. That's a respiratory alkalosis. And if CO2 goes down, bicarb must go down. And again, in respiratory alkalosis, you have a negative base excess. This one, CO2 rising, respiratory acidosis. CO2 goes up, bicarb must go up. There it is coming up, becoming, and you also see in all of them how you're becoming more normemic, heading back towards a normal pH, if normemic is a word. And then you have a positive base excess, and not to insult anyone's intelligence, the next one is metabolic alkalosis, and again you have a positive base excess. So the thing of that you may never have grasped before, that a negative base excess is seen both in the metabolic acidosis and respiratory alkalosis, there are two of them, and in positive base excess in respiratory acidosis and metabolic alkalosis. Now, why have I asterisked it? And I've asterisked it for the very important point that the system by Copenhagen Group was designed to measure the independent metabolic component. Therefore, the base excess is dramatically shifted by any metabolic disturbance, such that when you see the respiratory acidotic sort of patient in A&E who's breathing away, and you go look at the base excess and you go -5. Well, Dale said he's got to, look at that. He's obviously got a respiratory acidosis. CO2 is 12. How can he have a negative base excess? That's because the moment he gets a little bit of lactic acidosis build up, the moment he gets a bit of metabolic disturbance, he will shift the base excess dramatically towards the metabolic disturbance, not the respiratory one. So you've got to be a little bit careful with base excess. It's still very useful, but its disadvantage is it really only works in a test tube. It's actually the PCO2 independent indices are not independent in vivo in us. They're not really independent. They're all interrelated. And you can't really distinguish compensation from actually the metabolic disorder. So in some ways it's an eyeball, the base excess, but it's not very practical. I'm going to jump to number 3. Stewart. Anyone heard of Stewart? Some of you have. And some of you should get his original paper. It is amazing. You read it and you go, yeah, he's right, it's fantastic, it's amazing. And you get to the end and you go, and start again, and you just read it again. But he was a chemist from Canada. And he basically said, you guys, you've got it all wrong. We were taught in high school and even primary school that we are mostly made up of water. And water is always dissociating all the time from H2O into H plus and OH minuses. So with that huge bulk of water in our body, why would it make a blind bit of difference if a tiny bit of you dissociates into a H plus and OH minus? Why would it actually affect any system in the body when we are designed to be in water? That's where our cells are flooded with. And he says, this is all wrong. H plus is actually not really at stake here. And he also said the body has to be electrical neutral. Now, across a cell membrane, okay, you can have a difference in electrical potential, but overall your body has to, the pluses and the minuses must always be equal, or you're a battery. And if you're a battery, you're not going to live very long. Batteries aren't conducive to life. And he said, and I think he's absolutely right, that H plus is a dependent, and bicarb are dependent variables. They never alter anything, they're always altered. Things like independent variables in the body are like carbon dioxide, something called the strong ion difference, which is basically made up of, if you've got a bag of normal saline, there is no salt in there. There are Na pluses and Cl minuses because they're fully dissociated. And if you add up all of those ones there, you've got a gap of about 40. And they're always the fully dissociated ions in your body. And also things called the weak non-volatile acids, which are basically proteins, which are basically albumin. And he is my hero for these two reasons. He can explain why hyperchloremia causes an acidosis, and he can explain why low albumin causes an alkalosis. Now, traditionally, this used to take pages and pages in textbooks with very convoluted arguments, but he can just explain it in one diagram. Okay, here we are. You've got your cations, and you've got your anions. The strong ions are these ones, and this one, the chloride. And remember, albumin is an independent variable, chloride's independent, but bicarb is a dependent variable. So you go along and you keep giving your patient normal saline. Remember, it's got lots of chloride in. The body also must always be electrically neutral. So here we are, keep giving out chloride. What happens? Well, the albumin won't change. It's an independent variable as well. The body must maintain electrical neutrality. So bicarb, which can dissociate at any time pretty well into water and CO2, it gets shrunk, and if bicarb goes down, you've got an acidosis. And as simple as that, he can explain what is actually took ages and ages in textbooks to explain for why you can get what used to call dilutional acidosis. Likewise, a lot of our intensive care patients, you'll see, will actually have a drop in their albumin. And a lot of them then get a metabolic alkalosis. There are a number of other reasons for it, but look at here. Albumin goes down, chloride won't change, it's independent. Something's got to fill the electrical neutral gap, since CO2 and water is pretty well floating around in the body all the time, and you can just dissociate anytime you want, and therefore bicarb goes up and you've got your alkalosis. It's very cool for ward rounds and pontificating, but it's not very practical. So I think Stuart's almost certainly right, but I've never found a practical application for it apart from making people sweat on the ward round, the senior people, however, not the junior people, about sort of explaining all these sort of things. Let me tell you something that's more practical. The Boston rules, and we're talking Boston, Massachusetts, not Boston, Lincolnshire, in case you thought they came up with them. This was actual experimental work on humans rather than on blood in a machine. And what they do is they intrinsically incorporate the in vivo interaction between CO2 and bicarb. You don't need any nomenclature, it's basically just some rules. All you need the history, the pH, CO2, bicarb, and rules. Some of you, I think, are starting to hear these rules because, one, I've been harping on it for years, and also I think it is entering into people's thinking. Some of you will never have heard this before. They came up with rules, and because it was American, they're mainly in millimeters of mercury. The only one I'm going to teach you is this rule. In metabolic acidosis, the expected carbon dioxide in metabolic acidosis equals a fifth of the bicarb plus 1, which is plus or minus 0.3. And if any of you got MedCalc on your phones or devices, just go down to expected CO2, and there you'll have it. It's there on the MedCalc as well, so it's not just me making this up. And what this is doing is it's resetting the normal value for judging appropriate compensation. See, he was really easy. 1 up, 1 down, mixed process. And when you look at him, you can even see it. You can apply the rule if you need to, and you can apply a fifth of the bicarb. So a fifth of 19 is basically, 4 plus 1 is just a bit under 5, plus or minus a little error rate. And you can see he should be 4.8. He's actually 6.2, and so he's clearly got a mixed picture of respiratory acidosis because it's higher than it should be. But what happens when you see this? We can't do the 1 up, 1 down rule here for mixed process. They're both going down. But if you do put the rule in, you'll see that this gas, for that degree of metabolic acidosis, and see how the pH is normal? Because it's telling you it's mixed process before you even go any further. But you can put the rule in. She should be 3.4, she's 2.8, which means that she's much lower than she should be. And then again, you now, because it resets to normal, you can say this is a mixed process. This is a metabolic acidosis with respiratory alkalosis, 2 processes. Okay. Now I'm going to try to give you 3 cases to try to convince you that this is worth remembering. They're all real.